So the reason I wanted to give this lecture as part of this course is that you guys are about to go to your 5th year and then graduate. Most of you will enter optometry straight away after your degree. And right now, there is a big talk in optometry and ophthalmology about artificial intelligence and how it's being implemented and used all around the world. As we go through this lecture, you will see that, especially overseas, there has been a lot of advances in artificial intelligence in optometry and ophthalmology, along with other fields, and it will come to New Zealand. So sooner rather than later, you will see different implementations of artificial intelligence, especially deep learning, and we will go through what deep learning is in your practice later on. So I called this lecture Deep Learning, which is a form of artificial intelligence and optometry, the good, the bad, and the ugly, because there are many different sides to deep learning, and I believe you should know about all different aspects of artificial intelligence, especially when it sort of considers your profession. So what is deep learning? Deep learning is a subset of machine learning, and machine learning itself is a subset of artificial intelligence. So AI, or artificial intelligence, is some sort of a brute force approach to solve a problem. You have a problem, you try so many ways, like try to predict every single chess play. That's how AI works. That's the artificial intelligence, just brute forcing. Machine learning is about pattern recognition. So the computer programmer tries to identify a certain pattern in a certain image and then try to generalize it. Deep learning is how the human brain works. So how's that? Deep learning is a progressive autonomous pattern recognition process. That's exactly how the human brain works. So essentially, in deep learning, the programmer doesn't look for a pattern. The computer guesses a pattern, then tries to generalize it, and every time it makes a mistake, it learns from the mistake. So the computer improves on its own performance. It's totally hands-off. That's why this is true artificial intelligence. So imagine as a kid, how do you know that an apple is different to an orange? You try one and then the other, and they taste different. And then you try so many times that it becomes a pattern in your mind that these two are different. Right? So you can generalize that. That's how exactly deep learning is applied. In many different tasks, like image recognition, language processing, or translation, deep learning relies on that pattern recognition. You got a deep learning application on your mobile phones right now. When you say, for example, OK, Google, show me the next set of movies, Google will come up with a series of movies for you. But what if you say, OK, Google, what's the next, like the closest cinema? A different sentence about the same thing. But Google recognizes that. And that's deep learning, because it's not about the word cinema or movies. It's about the pattern. So that's how they implemented it. You will see that this is how exactly it's used in optometry and ophthalmology. But for pattern recognition, you need a large data set. For example, when you're talking about natural language processing, you have to have all the words that relate to watching a movie. Movies, cinemas, I don't know, new releases, Hollywood, all of that. And then you combine it to create a large data set, same as images. So I will come back to this point about a large data set that is necessary for any deep learning algorithm. So why do we call it deep? As I said, deep learning is about pattern recognition. Deep learning is a set of, as we call them, layers. Layers are essentially different convolutional algorithms. Each layer is trying to figure out a single pattern. So you have so many layers trying to figure out all the patterns that exist in a sentence or in an image. So every layer is about a single pattern, and when you have too many of them, it becomes a deep network. Essentially, the more layers, the deeper the network. It means that it looks for more patterns. This is another fact that I will come back to, but to give you an example, the first artificial intelligence, the first deep learning algorithm, had about 10 layers. The ones that we are working on today in this faculty, in my research lab, they have about 300 layers. So those are the number of patterns that you're looking for in a single image. So that's why we call them deep. As I said, in every image that is, so deep learning and images, we're talking about recognizing a pattern. So say this is the input image, right? A human face. What are the patterns that a computer can look for? All of those. So every little tiny tile in that image is a single pattern that the computer has recognized for that face. To look at it a bit closer. So this particular pattern, so this is one of the layers. Remember, deep learning has many layers. One of the layers seems to be sensitive to the eyes. So it can detect blinking. So you can generalize that about everything that would change in an image, being a human face or a fundus photo. And we will have examples of it a bit later on. So coming to the theme, the good, the bad, and the ugly. So there are three different aspects of deep learning and vision science and optometry and ophthalmology, and the three of them are very different. The first one, and I start with the good, is the research. To me, the good side of artificial intelligence is the research part. There are so many exciting things that are happening in research of deep learning. For example, you might have already heard of IBM Watson. That's the sort of neural network that is developed by IBM. And it's implemented in several oncology departments, especially in UK. So when the patient comes in, Watson sees patient's record, Watson sees the lab results, and Watson essentially designs a treatment protocol for that particular patient. It seems that Watson is as good as all the human oncologists. So then the question is, would IBM Watson replace radiologists? I don't know the answer to that question, but we will see. Another company called Deep Genomics. They linked all the large data sets that are available for DNA and tried to link all the medical records of people suffering from different diseases of sort of genetic background. So they come up with this cool bank of data that you can go to, enter your DNA, and it will tell you if you're susceptible to all these different diseases. The Atomwise was another company. This was the company that essentially stopped the Ebola pandemic. When Ebola became a problem several years ago, we didn't have a vaccine for it. And we didn't have the time to develop a vaccine. So instead of going to go down the traditional route of developing a vaccine, going through clinical trials and all that, they ran a deep learning model on the vaccine and figured out 2 different drugs that could work. Normally, developing a vaccine takes about 10 years. They developed this thing in less than a year, just by deep learning process. Another company called Arteries. Arteries, they developed a pattern for monitoring the heart. So when you go and have a 3D CT scan of the heart, This particular deep learning figures out the configuration of the arteries around the heart, and it can predict cardiovascular problem. So it's about prognosis. So FDA, which is the governing body of all the medical devices, as you might know, already has a team of software engineers. And now they essentially approve AIs as devices. So a computer program is not a program anymore. It's a machine. And if it's a machine, it can be implemented in a clinic. And that's the difference. So several AIs have already been approved as clinical devices by FDA. So what about vision science? And this is the bit that is more relevant to you guys. I want to give you examples of deep learning in optometry and ophthalmology. For example, the starting point is optometrists and ophthalmologists rely a lot on pattern recognition in images, being OCT, fundus photos, any other form of imaging. But that's really good for any deep learning algorithm programming, because, as we said, deep learning is good in pattern recognition. So the idea is that if we essentially implement deep learning as a screening and diagnosis tool, then the clinicians can focus more on patient interaction. That's my personal belief, and I think that's where the field is going. And we will see how this develops through the lecture. So for example, in detecting cataracts, one study showed that it can grade nuclear cataract based on slit lamp images. And the absolute error was about 0.3, which means it was correct 70% of the time. It outperformed several clinicians, which means that out of a group of humans, it outperformed most of them. Another study, they trained a neural network on slit lamp images of pediatric cataracts, and it matched the performance of pediatric ophthalmologists, which means it performed as well as a pediatric ophthalmologist. In glaucoma, there was a study that used fundus photos of the optic nerve and for detecting glaucoma, and it achieved about 83 to 87% accuracy. Another model used OCT images, disc OCT images, and it achieved 93% accuracy in detecting glaucoma. Another study looked at the preparametric visual fields to detect glaucoma, 92% accuracy. And these are accuracies against an ophthalmic performance. So an ophthalmologist was trained to do this, and then deep learning network is trying to match that performance. Macular degeneration. So this was an interesting study. They showed 130,000 fundus photos to the computer. These photos were previously graded by retinal specialists for 10 different retinal diseases. Deep learning algorithm essentially achieved between 88 to 91% accuracy depending on the pathology. Another study used 50 healthy and 50 neovascular AMD patients to predict AMD, and it achieved 100% accuracy. So there's a problem here. 100% accuracy. Nobody is 100% accurate, not even a computer. And this is the problem, one of the problems that I will come back to when we talk about artificial intelligence shortcomings, and that's a small data set. The first study, which was 91% accurate, used 130,000 images or 100,000 images. The second study used 50. So achieving high accuracies and high repeatability is not difficult if you have a small data set. So that's one of the aspects of deep learning that's misunderstood. People throw around these numbers very easily, high accuracy, high sensitivity. What is missing is a good sort of validation test out there with large population. That is not happening just yet. This is one particular study that I liked. So there is a group at Singapore National University, and they've done a very good research in deep learning, especially in ophthalmology. They trialed their neural network in Singapore and US. They used fundus photos and looked at detecting glaucoma, macular degeneration, and diabetic retinopathy in those fundus photos. So the study is multi-center, multi-ethnicity, multi-device, which is a sign of a good study. 14,000 images, 14,000 patients, 71,000 images, and at least 2 ophthalmologists grade each image. So how did they do? And by the way, these are the gradings that the study came up with. So different diabetic retinopathies and AMD and glaucoma grades. About 90% accurate on all of the cases. So that is a study that I can trust. Large number of images taken in different hospitals around the world from a multi-ethnic population. The same group took their deep learning algorithm and run it in Singapore, in China, in Mexico, and in Hong Kong. So almost all around the world. And if you look at the accuracy, which is this column, every time it's close to 90%. The external validation is the Achilles heel of deep learning. Again, people throw these numbers around very easy. Don't let them impress you, because it's quite difficult to get a network to work all around the world. It's easy to do it in a small study. Same study, so these numbers are for diabetic retinopathy. Same study achieved more than 90% accuracy for glaucoma and more than 90% accuracy for macular degeneration. So that is a good study that I can trust. There was a follow-up study of the same group. This was literally less than a month ago. They reran the program, used 18,000 new patients, 19,000 new patients. 8 different centers, again, around the world, and used it to detect 3 degrees of diabetic retinopathy. And as you can see on the plot, every time the machine matched the human. Every time. And by the way, they used 17 different human graders. So out of the 17, the machine matched all of them on a large multi-ethnic data set. Is that the impressive part? Yes, but it gets more impressive. Humans, and in that particular study, took 3,600 hours to grade those images. AI took 51 hours. So that is the impressive part. The fact that the AI not only can match humans, it can improve the performance by more than 60 times. Out of all of those images, about 8% were not gradable, which means low quality. So the images were low quality to be assessed. Humans took additional 123 hours to grade that 8%. So I believe that is where the role of the human will stay within optometry and ophthalmology and in other fields. Assessing situations that the computer cannot assess. More specialized cases. Because for the majority of cases, the artificial intelligence will be able to match the human performance. There are So that's only one group. There are several groups around the world that are trying to replicate the same thing. So I don't know if you've heard of DeepMind Health. DeepMind Health is a UK-based company and was the first company that developed a commercial ophthalmic AI. They trained their network on 15,000 scans from Moorfield Eye Hospital, which is the largest eye hospital in the world. And the network can detect 50 different eye diseases from OCT and fundus photos. So this is the sort of the images that the DeepMind network sees. NFAS OCT as well as the original OCT machines. And then the machine generates maps like this. So the machine essentially tells the clinician what are these bits are. So it can detect different things that could be wrong with an OCT image. And by the way, the machine is about 100 times faster than humans. I love this plot. This is amazing. So when they first published their results, the left-hand side is what they call the area under the curve plot, which is essentially specificity and sensitivity of the network. The higher you are, so the closer you are to 100%, the better, right? So the blue line is the performance of the machine, which starts at 0. So here at the beginning, the machine is learning. And quickly, it reaches about 100%, right? So it quickly reaches 100% and it stays about 100%. The company, DeepMind, they recruited, I think, 8 different people, 4 retinal specialists, so 4 ophthalmologists, and 4 optometrists. And the number on the side essentially shows the years of experience. And they ran the network against those 8 individuals. Here's the right-hand side is the zoom in of this part of the plot. If you pay attention, the network, which is in blue, outperforms 6 of these guys, which means out of the 8 humans, the AI can beat 6 of them. The only 2 people that are better than AI are the 2 top ophthalmologists. It's a known fact. More experienced ophthalmologists or professionals are better than junior ones, right? So the AI, by matching the best of the humans, is outperforming all the average ones. And I think that's the big message here. If this is happening, not only in optometry and ophthalmology, but everywhere, it's a bad time to be an average clinician. You want to be at the top of your field. So this is another cool part of the deep learning. So not only machine can predict these diseases, it can also hint the clinician where to look at. So after the machine has made its prediction, you can essentially delve a bit deeper. So you can treat the neural network as a black box and just ask for answers. Or you can use it as a guide. So the network will highlight. So these are the highlights that are generated by the machine. It can highlight the problematic parts of a photo, for example. So not only it can help the clinician by giving the clinician the grade, it can also help them by saying, hey, look at here. Something is wrong here. So it can do extra. And I will come back to this a bit later. But I want you to sort of notice that term, attention maps. These are called attention maps. Sometimes they're called activation maps, but I like attention maps. I will come back to this a bit later. So that was the good. Everything shiny, the AI is going to replace all the human beings, and we're all going to be redundant. That's not true. Because now we're getting to the bad part, which is clinical implementation. So it's all good and well when we are designing an AI in the lab at the university. How are we going to implement it in a working clinic? So Google is at the forefront of this. Google has tried so many times with many different networks to implement it in different settings. So this is a new study. They ran it, I saw the paper last month. They tried to implement an AI alongside 10 ophthalmologists in an eye clinic, and I believe it was Morfield Eye Hospital. So 10 ophthalmologists, either they graded diabetic retinopathy images unassisted, which means by themselves, assisted by AI, and AI just give the clinician the grade, or assisted by AI where the clinician was given not only the grade, but also the heat map. So they wanted to see if this will help the clinicians perform their daily tasks. So these are the things that the clinician would see. If they were unassisted, they will only see the fundus photo. If they were grades only, they will see the fundus photo and the grades suggested by the machine, so the human can override that. If they see the heat maps, they see the areas of the image that the computer is interested in as well, so they can have a closer look. So what do you think will happen? So graders or human readers graded more accurately when assisted by AI, when they saw the grades only. Graders that used the artificial intelligence grade plus heat map had reduced accuracy in cases that there was no diabetic retinopathy. So their performance decreased in healthy cases. The reason for that is the computer always generates a heat map, even if there's nothing to see, because it always finds a pattern. That pattern might be nothing, but clinicians could overestimate. They can say, oh, maybe that's something wrong. Maybe as a human, I'm missing something. So the performance in detecting the healthy cases actually dropped in humans. So that's one of the barriers in implementation of AI. How do you gel these two, humans and AI, without compromising the general performance? The clinicians that got the grades only, they had increased sensitivity, so they had fewer false negative cases. So what I want you to see here is that these are 4 different cases. I found that very interesting. These are 4 different cases. And these tables right below, they show the human grades versus, the unassisted grades versus the grades only. So I want you to focus on the red dots versus blue dots. In images that were easier, most of the times they agreed. So for example, here. In images that were more difficult, most of the times they disagreed. So the human graders were all over the place when they were unassisted, whereas the assisted humans were always on the same point. So AI not only enhances the accuracy, it also increases the repeatability of the human performance. So the humans that are assisted by AI become more reliable. What was the downside? So the downside was that the whole process slowed down the ophthalmologists, considerably so. So the time taken for grading a single image when unassisted was 50 seconds. When assisted was about 70 seconds. So about 30% decrease in performance, time performance, I mean. Clinicians did get faster. So the study mentions that they did get faster with more practice, but they never reached the speed of the clinicians that did not use AI. But now the question that Google is asking is, well, whose fault is it? Is it the fault of AI that the humans are slow? Again, that's another question that we don't have the answer to yet. Another problem with artificial intelligence, and this is always sort of been ignored, is that AI, although it's all good and well, it can be fooled very easy. There's a thing called adversarial images. Adversarial images is when an image is changed by a tiny amount. So the images on the left-hand side are exactly similar to the right-hand side, but 5% of pixels are changed. To a human eye, they're exactly the same. To a computer, they are completely different. The reason being is that, again, computer is looking for patterns, and it becomes so good that 5% change will change the decision of an AI. But whereas humans, they look at the general pattern. So a bit of change here or there doesn't make a difference to a human eye. So humans are actually much less sensitive to this adversarial effect, or to essentially noise. Whereas AI can be easily fooled if there are those adversarial images. So look at this. So the original AI had 98% accuracy. By 5% change in the image, it dropped to 50% accuracy, which is essentially chance. If you flip a coin, that's 50%. The clinical expert was not affected at all. So humans can easily outperform AI when the images are lower quality, right? So that's something else that is missing when people talk about AI. This is a study published, I think, about 2 or 3 months ago, where Google ran a similar trial that they did in UK, but this time in Thailand. Thailand is as you know, is a low-income country. They have a lot of problems in their primary health, and they are very keen in taking up AI for their medical care. So they graded about 25,000 retinal images, and essentially they got a team of international ophthalmologists from Thailand, from UK, and other places to grade them. So relative to human graders, AI achieved a higher sensitivity. So actually, AI was more sensitive than humans. And also about the same specificity. One reason, and I saw that in the paper, was that they mentioned because their team of ophthalmologists were international, different countries have different training methods, and different ophthalmologists from different jurisdictions have a different sort of skill set. So they're not going to match each other, whereas AI is going to perform the same all around the world, right? But again, these numbers were a bit too good. So I look at the paper and I was like, that's a bit too good for something that is sort of, 20,000 people in Thailand where I know the quality of the images are not that great. We're not talking about a well-funded hospital in UK. We're talking about images in the middle of Thailand, which the devices are not as great. So what's the trick? The trick is, first of all, they combined all the healthy participants' data with the mild diabetic retinopathy. So everybody that was not deemed referable was treated as healthy. So that's a big problem. The other one is that they excluded a lot of images. So when you exclude a lot of images, of course your result's going to be good because you're dealing with good images. So that's not realistic. That's one of the problems that Google and other companies have implementing AI in the real world. Because in real world, good images are not that common. If you're taking photos in a rural sort of community using a less than optimal camera, AI is not going to work. Again, that's one of the parts that the human can easily outperform. Humans are better dealing with low quality images than AI. Oh, by the way, I love this image because this is the new way they're going to monitor exams. Silent drones, that's real. So that was the bad. So the bad was clinical implementation. What about the ugly part? The ugly part of artificial intelligence is about regulations and commercial interest. So here are some examples that things went wrong implementing AI. DeepMind, the company that I already told you about, it was founded in 2010. They got in a collaboration with Moorfield Eye Hospital pretty quickly and, quote unquote, mined data out of Moorfield Eye Hospital. So they had a sort of an agreement, sort of a handshake with the hospital. So we use your data to develop our product. And the hospital, being nice clinicians, says, yes, of course. The problem is DeepMind didn't tell the hospital what exactly or what sort of data exactly they're going to access. So they essentially helped themselves to all the data they could gather. It resulted in a lawsuit, and Google later on bought DeepMind and paid the fine for $900 million, which is nothing for Google, by the way. So that's one problem. When you are giving AI data, what about privacy? Did the patients agree for the data to be analyzed by an AI? We haven't figured out that yet. Now, DeepMind is still making progress. They have created this app called Streams. And I believe it's available mainly in UK. And using Streams, it reads in all your medical data, and it's an opt-in sort of app. So now they've sort of figured out the ethics part. And Stream then analyzes all your medical data, put them all together using AI, and then it can essentially alert your nurses and medical doctors for when your sort of vital signs become abnormal. So imagine your Fitbit or wearable watch connected to an AI, and it can detect the problem, alert the local nurse or a doctor. Sounds all good and well. However, again, they help themselves to a lot of extra data. So for example, where did you go? What did you shop? Did you shop healthy food or rubbish food? They had all that data. And again, they got to a bit of a problem with the courts in UK. And I got that quote out of the judgment against DeepMind. This was a judge telling DeepMind that the price of innovation does not need to be the erosion of fundamental privacy rights. So on its face, this app can do amazing things, but what's the price? The other thing was that prior to this court case, Google promised that DeepMind will be for scientific purposes only, right? And everybody believed Google. Well, right now, DeepMind Health is the main arm of Google commercialization in medicine. Another problem with AI, and this is very new, it's called re-identification. So there was this study in 2018 that showed, based on a single fundus photo, not only you can detect disease, you can detect all of these different parameters about that person, the age, the blood pressure, their smoking habits, and also gender. So if you combine all of that, wouldn't it become re-identifiable? So these images are supposed to be de-identified. The computer should not know who the patient really is. Only the clinician, the human, should know. But given the fact that now AI can figure out all of these from a single photo, couldn't it be then traced back to a single or a very small group of people? What are the ethical implications of that? So right now, different jurisdictions are looking at it and see if re-identification is going to be an ethical issue. To give you an example, this is, I believe, a Dutch company. It's a company that uses AI, which again mines all the clinical data, and it links it to the patient's record, and then, quote unquote, helps caregivers and hospitals to avoid unnecessary hospitalization. What does it really mean? It really means that this company essentially tells the hospital, oh, this guy might unfortunately die soon, so you may not admit him. That actually happened. Or this guy is going to suffer from a cardiac arrest in the next 4 or 5 months, so you may not insure him. This is really happening. And these are the ethical problems that are happening alongside AI when the computer knows too much about us, and not only about our current state, but our future. If the computer can predict that somebody's going to have a cardiovascular problem, and then they sell that data to an insurance company, how can we stop that from happening? Another part of AI that is still work in progress and is still happening is called benchmarking. So benchmarking it's been around forever. It's essentially assessing the performance of a certain, I want to say clinician, but it could be anybody, against everybody else. So I've got these quotes from different CEOs and heads of companies in optometry. So Specsavers, Bailey and Nelson, all of those. And essentially what all of these quotes are saying is that benchmarking is happening in optometry in New Zealand. So when you go out there, if you work for some of these companies and some more that are not mentioned here, your performance will be benchmarked against everybody else. Specsavers already published that. The number of, for example, referrals per practice, the number of patients seen. Benchmarking in itself is not an issue. But how do the companies go from here? So if they have access to the data from a branch, what stops them to access data from a single clinician? So again, although benchmarking can be very useful, if done poorly, it can lead to a lot of problems. So that's another issue with AI. So there are lots of questions when it comes to ethics. And again, that's the ugly side of artificial intelligence. Who owns the medical data? Is it the clinician, the patient, the hospital, or a combination? Who owns the AI-generated data? Is it the company who developed the AI, the researcher who developed the AI, or the clinician, or the patient? In the case of misdiagnosis from an AI, who is responsible? The software engineer? I don't think so. So since AI is much cheaper and much faster than a clinician, there is a push from a lot of insurance companies, among others, to implement AI in different fields. But AI, as I mentioned throughout this lecture, is not fully tested. It's all good and well in a research lab, but there are huge implications when you take it out of a research lab and try to implement it in society. So then the question is, for example, will insurance company pay for AI misdiagnosis? That's a big, big question. Who's going to pay if an AI misdiagnoses somebody? So all of these are questions that are not answered, and I don't think they're going to be answered anytime soon because there are a lot of stakeholders, as you can see, in this field. So I want to finish on this remark. So I believe that AI will not replace clinicians, you guys. But it will replace those clinicians who cannot work with AI. So the wave of AI is coming. It's already happening. I believe as future clinicians, you should be able to work alongside AI. Because those of you who are not ready for that will be caught by change. Thank you. If you got any questions, feel free to ask. If you are interested in knowing more about AI, like Anne, for example, is doing a very good research on AI, just come and ask me, and I can give you more material to read. All right, thank you, guys.